Good afternoon, everyone. I'm Yiyao Gong from the Bartlett School of Sustainable Construction at University College London. This presentation is based on a paper co-authored with my supervisors, Professor Tim Broyd and Dr. Carlos Galera-Zarco. I will be discussing how BIM can be understood in terms of its integration capabilities to support supply chain integration in construction. The construction industry still faces persistent fragmentation across project phases and organizations. This fragmentation limits coordination and obstructs knowledge flow. BIM has been widely promoted as a technological enabler of integration in response to these challenges. Yet, there is limited understanding of specific capabilities through which BIM supports supply chain integration. These form the basis of the research. This study is guided by pragmatism and an outcome-oriented perspective, focusing on how BIM supports supply chain integration in real project settings. BIM-enabled integration practices are used as proxies for BIM integration capabilities. These are BIM-facilitated practices that directly contribute to integration outcomes. Two mechanism types are examined. BIM technical mechanisms refer to core BIM functionalities and internal processes. Complementary technical mechanisms refer to external tools and technologies that extend BIM's integration capabilities. This framing helps to understand how integration is achieved through practices and technical mechanisms. This study aims to identify the integration capabilities of BIM for enhancing supply chain integration in construction. To guide this investigation, 4 questions are addressed. First, what are the capabilities of BIM to facilitate supply chain integration in construction? Second, what BIM-enabled integration practices demonstrate BIM integration capabilities? Third, what BIM technical mechanisms underpin BIM-enabled integration practices and thus BIM integration capabilities? And fourth, what complementary technical mechanisms enhance BIM-enabled integration practices and in turn BIM integration capabilities? These questions shape the direction of the study and inform the review strategy. This study uses a systematic literature review based on Tranfield's framework, ensuring rigor and transparency. A scope search from 2010 to 2025 targeted the intersection of BIM and supply chain integration. After screening, 13 articles were selected using strict inclusion criteria. Semantic synthesis was applied to identify BIM-enabled integration practices, BIM technical mechanisms, and complementary technical mechanisms. Manual coding linked these practices to integration types, forming the basis for the framework introduced next. Based on the review findings, this study introduced the BIM integration capability framework, which is the central conceptual outcome of this paper. It outlines how BIM facilitates supply chain integration in construction by organizing BIM integration capabilities into 4 distinct pillars: information, process, relational, and technology. Each pillar is illustrated by BIM-enabled integration practices that show how integration happens in practice. These practices are supported by BIM technical mechanisms and further enhanced by complementary technical mechanisms. This layered structure bridges theory and practice. Next, I will show some examples from information and process integration. This practice supports information integration, and the focus is on tracking building element status. It helps align CAD, ERP, and BIM systems to synchronize status data across design, prefabrication, and construction phases. This alignment enables real-time visibility into production and delivery progress, helping to overcome fragmented data structures. It enhances planning precision by keeping all actors updated. Automated data exchange forms the technical foundation for BIM's information integration capability. It embeds real-time material demand into structured project environments by synchronizing updates across supply chain actors, enabling timely adjustments and reducing mismatch risks. This practice is This mechanism underpins the practice of synchronizing demand fluctuations with 4D BIM, which demonstrates BIM's information integration capability by linking look-ahead plans and site data into a connected environment. Through this, contractors and suppliers can access same up-to-date information, allowing informed and coordinated supply decisions. A cloud-based common data environment enhances BIM's information integration capability by enabling suppliers and contractors access validated and real-time material demand data. This helps prevent fragmentation and supports continuous coordination during demand changes. This mechanism becomes especially effective when applied in the practice of synchronizing demand fluctuations with 4D BIM. Previously introduced, which connects look-ahead schedules with real-time site data to enable dynamic and data-driven supply adjustments across the supply chain. This practice supports process integration, and the focus is on embedding look-ahead planning in BIM-enabled change coordination. It aligns material and task schedule across design, production, transport, and installation phases by embedding iterative look-ahead planning cycles and milestone-based task updates. It is especially useful in engineer-to-order workflows, where design or planning changes often occur at later stages. Through BIM-supported real-time coordination, task sequences and production plans are dynamically adjusted, demonstrating BIM's process integration capability. This capability is underpinned by automated quantity takeoff, which ensures that suppliers material quantities remain consistent with the evolving task schedules. As the parametric model changes, the system automatically updates the bill of materials and the planning data, allowing smooth alignment between planning and execution. This mechanism guarantees continuous integration of material and task data throughout look-ahead sessions, enabling supply chain actors to maintain synchronized operations even under frequent change. RFID-based material tracking enhances BIM's process integration capability by linking the physical movement of engineer-to-order components with BIM-based task adjustments in real time. During iterative planning, the system allows planners to compare actual material flow with developing design, production, and installation schedules. This tight feedback loop supports continuous coordination, especially under late-stage changes, enabling BIM to integrate process flows across phases more effectively. Due to time constraints, this presentation focuses on the information and process integration. The remaining two, relational and technology integration, are addressed in the full paper. To conclude, this study defines BIM integration capabilities across 4 key dimensions: information, process, relational, and technology integration. It develops the BIM integration capability framework, which links these capabilities with technical mechanisms and integration practices. This promotes capability-based thinking in BIM implementation and provides practical guidance for selecting appropriate practices and tools to support supply chain integration. This framework also lays the foundation for future research aimed at validating these practices and further exploring the role of complementary technical mechanisms. These are references used in this presentation. Thank you very much for your attention. I look forward to your questions and